All right, buckaroos, now here we go. We're going to talk about taking 50 grams of water. Now write this down. 50 grams of water at STP, and we're going to take it from, let's say we're down here at minus 10 degrees. I'm going to make that pretty steep. And so what we're going is going from minus 10 degrees down here, and then we're going to go to 0, and look what happens at 0. The temperature stops rising. She goes flat, the line goes flat, and we're melting it right here. That's the heat of fusion, okay? Then we're going to take this liquid water over here, and I'm going to make this slope a lot different because it takes a lot more energy to raise the temperature of liquid water, okay? And we're going to go up to 100 degrees, and then look what happens. She goes flat again, okay? And then that's while it's boiling, and then once we've converted it all to steam, then the temperature starts to rise again, okay? So again, what we're saying we're going to do here is we're going to take this 50 grams of water at minus 10 degrees. Of course, it's ice down here. It's a solid here. And then we're going to take it up here to 0 degrees. Well, at 0 degrees Celsius, ice melts, right? Standard conditions. And so then this whole phase right here is the liquid phase. So we're going to go from 0 degrees across here, and this is going to be 100 degrees, okay? And then we're going to boil it. Starts boiling right here, and all the way across this line right here is the point where it's boiling. You notice that during these phase changes, the temperature does not change. As you continue to add heat energy here, the most energetic particles leave and become vapor. That tends to lower the average kinetic energy, but because you're continually adding heat energy, that tends to raise the kinetic energy, so the average stays the same. And we measure temperature as average kinetic energy, okay? But as soon as we get it all to vapor, then whoom, the temperature starts to go up again, and pretty rapidly, okay? So we're just going to say, for the sake of this problem, we're going to take it up to 110 degrees Celsius, okay? I'm going to use 1 decimal place there. So what we have here then is temperature on the y-axis, which we know is measuring average kinetic energy. And on the bottom, we can say on the x-axis, we'll say we're measuring in time, but really what we're doing is we're going to be measuring, it's going to be time, and then we're going to be subjecting this to energy, some quantity of energy per time. So when we multiply by time, the length, the actual length of this line along the y-axis will be energy. In other words, the distance from here to here will be the amount of energy, will be representative of the amount of energy required to increase the temperature of ice. The difference from here to here, from that distance to that distance, will be the amount of energy associated with melting the ice. The distance from here all the way to here is the amount of energy required to increase the temperature of the liquid. And then from here to here is the energy used in converting the liquid to vapor. And then I didn't draw my y long enough, and then from here to about here is going to be the amount of energy required to increase the temperature of the gas, okay? So this is the solid, this is melting right here, and we're going up the hill, okay? This is the liquid phase, and then this is boiling. Okay, this is boiling, and then here is the gas phase, okay? So we're going solid, we're heating up the solid ice until we get to the melting point. Then we're melting the ice. Okay, now we've got all liquid right here, so now we're heating up the liquid here. And here we've reached the boiling point, okay, where the vapor pressure equals the surrounding pressure, and we start converting it to gas. All of this distance and time right here and energy right here is converted to dedicated to converting this liquid to gas. Then we hit the gaseous phase, and the temperature of the gas begins to increase. So what we have here, what we want to know is how much energy does it take to take this 50 grams of ice at minus 10 degrees to 50 grams of gas, steam, at 110 degrees. And what we have to do is calculate this in 5 steps. The first step is changing the temperature of the solid. The second step is melting. The third step is increasing the temperature of the liquid. The fourth step is the boiling. And the fifth step is increasing the temperature of the gas. Okay? Got it? Got it? Now, a couple of things we got to introduce to you. In your book, you saw that the energy associated with changing from a solid to a liquid is called the enthalpy of fusion, and the symbol for enthalpy is that uppercase H. For our purposes, we can just say it's synonymous with heat, and so the way you write that down, the variable is the heat of fusion, FUS. It's abbreviated FUS. And the heat of fusion is different for every pure substance. For water, the heat of fusion equals 6.009 kilojoules per mole. Okay, so for you to calculate the amount of energy associated here, you're going to have to multiply this by the number of moles. Okay, so how many moles do you have here at 50 grams? 50 grams of water. And you're going to convert that to moles. It's 1 mole per 18.02 grams. So that gives you how many moles? Do the calculation right there. How many moles is that? All you do, just like we've been doing for ages now, is divide the 50 grams by the 1802. Somewhat less than 3, 2.775. Okay, so this is going to equal 6.009 kilojoules per mole multiplied by 2.775 moles. Okay, and that gives you what's that come out to? 138, and you got to remember now this is kilojoules. 138.75 kilojoules. You agree with that?
I got a 16 point.
You're going to multiply 50 grams. You're going to divide 50 grams by 18.02 grams. That gives you the moles of water. 2.775 moles of water, right? Then you're going to multiply the 6.009 kilojoules per mole. That's the heat of fusion. Multiply that by your 2.775 kilojoules. By moles. 6.009 kilojoules per mole. And you multiply that by the 2.775 moles of water. Do that for me real quick and see what you come up with. Now, up here, it's the exact same thing, except instead of using the heat of fusion, you're going to use the heat of vaporization. Okay? And by the way, this in your book is on page 346, and this is on in your book on page 345. Okay? But the heat of vaporization for water, now look at this, is 40.79 kilojoules per mole. Okay? And so you see that this 40.79 is almost 7 times greater than this. Well, this line should be almost 7 times longer than this. I don't think I got it quite to to scale there because I was trying to make it fit.
350 and 351.
Alright, so we must have had a little brain cramp here. So what we did again is we took the 50 grams of water and we multiplied it by 1 mole of water per 18.02 grams. We come up with 2.775 moles of water. So here we know that the 6.009 kilojoules per mole is the amount of energy required to melt water, solid water. And so we multiply the heat of fusion, kilojoules per mole, multiplied by the moles that we have, and we end up with 16.65, and these are kilojoules. Okay? Now, up here, the heat of vaporization, we said, is the same idea, except it's heat of vaporization instead of heat of fusion. This is on page 345. The heat of vaporization for water is 40.79 kilojoules per mole. So we're going to have to multiply this by moles of water. The moles of water doesn't change. It's still 2.775 moles. So this gives us 2.775 multiplied by 40.79 gives us what? What do you get? I got 113.19 kilojoules. Okay? 113.19. So there's step 2 and step 4. Okay? Now step 1 involves a different property of water. And we have to look at this property of water in the solid phase, the liquid phase, and the gaseous phase. And this is called specific heat. The discussion on specific heat is in your textbook around page 530, something that's in chapter 16. But the specific heat is defined as the amount of energy. Look here, the equation tells you the variable is Q, and you can think of that as energy. We haven't talked about the unit yet. We're going to use joules and kilojoules. But specific heat is the amount of energy required to change the temperature of a given mass of a pure sample by a number of degrees. Usually it's Celsius, okay? So the units we're going to use are going to be joules, okay? And the specific heat of ice is 2.06 joules. And we're going to specify the mass as grams. So for every gram and every degree Celsius that the temperature changes. Okay? So this is the specific heat of ice. And we probably should specify that down here as ice. Okay? So now what we're doing here is we're solving for, I'll put a highlighted here with red, we're solving for Q. That's what the question is really asking. This is how much energy, right? So if we look at this equation where Cp, specific heat, equals Q over m times delta T, right? Then Q equals what? Then Q is going to equal the specific heat multiplied by the mass times the change in temperature, right? So for our case right here, it's going to be 2.06. Now this is where I've been telling you all along, you got to follow these units. This is 2.06 joules per gram degree Celsius. You're going to multiply that by our mass, which is 50.0 grams. And the change in temperature from minus 10 to 0 is how many degrees? 10 degrees Celsius, right? Yes? And that comes out to, multiply that out, and what do you get? You get 2.06 times 50 times 10. And that comes out to 1,030, I believe. 1,030. 1,030. I'm going to make that a little bit neater. Okay, that comes out to 1 joules. Now notice, this is joules, this is kilojoules. Okay? So when it comes time to total these up, don't forget we got a unit mismatch here, okay? So this is how we solve for the amount of energy required to change the the temperature from -10 to 0. And it's going to be the same thing as we change the temperature from 0, look here, to 100. The only difference is the specific heat of liquid water. Okay? I guess I should say it the other way around. I should say the specific heat of water as a liquid is 4.18 joules per gram degree Celsius. Okay? So this is much more. Okay? Twice as much energy, and that makes sense because here all you're doing is disrupting the particular orientation of the water molecules. You're not breaking the attractions. Here what you're doing is increasing the velocity of the molecules, and you have to overcome those attractions to increase the molecules. Now up here, the attractions are already broken as it's a gas, but here the attractions between the molecules are very strong, and so they have to be overcome before you can increase the kinetic energy. In other words, increase the velocity of the particles. So it makes sense that that's high, right? Okay. So again, same thing. The energy is going to equal the specific heat, 4.18 joules per gram degree Celsius, multiplied by the same 50 grams, right? Multiplied by, this time, what's the change in temperature?
In 0.
Nope, it's 100. We're going from 0 degrees right here, look here, 0 all the way up to 100. So it's a 100-degree temperature change. And that's going to give us a much larger, this is going to be a huge step in terms of energy, okay? So it's going to be 4.18 multiplied by 50 multiplied by 100, okay? And that's going to be 20,900 joules. You agree with that?
Yeah.
20,900 joules. That's step 3. Step 4 we've done. Step 5, let's move over here and do step 5 over here so we got enough room, okay? Step 5 is going to be the specific heat of water as a gas, okay? And that is 1.87 joules per gram degree Celsius. We multiply that by the 50 grams by, what's the temperature change here for the gas?
110
Nope, we're going from 100 to 110.
is 10.
10 degrees Celsius, okay? So we multiply that out, and what do we get? 1.87 times 50 multiplied by 10 is 935 joules, right? You agree with that? Did you do it?
Yeah, I got the 936.1.
935 joules. So when we want to talk about the total amount of energy required to go from -10 to 110, we're going to take our calculations, our energy calculations for each of the 5 steps and add them together, okay? Now, the first thing we got to do is convert these to the same unit. And the way to convert them to the same unit, look here, is we're just going to move this decimal back 3 places, okay? Move this decimal back 3 places. This one's already kilojoules. This one's already kilojoules. Okay, we've already got 113 kilojoules here, right? Okay. 16.65 kilojoules. Here's 1,030 joules. We move this back 3 places. Then we have 1.030 joules. So all we have to do to calculate this answer is we're going to say that the total energy total energy is going to equal the sum of step 1 plus 2 plus step 3 plus step 4 plus step 5. Right? You got it?
Yes.
Okay. So what is that? Our bottom step, our first step there from the ice was 1.030 kilojoules. Remember, we converted everything to kilojoules. Here we were already in kilojoules, 16.65 kilojoules. Here we convert this. This is going to be 20.90 kilojoules. Here we had 113.19 kilojoules. That's step 4. And step 5, I believe, was 0.935. Yes, step 5 up here is 0.935. 0.935 kilojoules. Okay? So we total that up, and what do we come up with?
552.7.
We got 5, and then 8, 9, 17. That's 20, right? It's 8, 17, 18. 27, that's 3, 9, 12, that's 2, 4, 5. So 152.705 kilojoules. Is that what you come up with?
Yep.
Then we got to round it to how many significant figures? 3 because of our mass, okay? So we're going to drop this to 3 significant figures, and what do we come up with?
153.
153 kilojoules, okay? And that is all there is to these heating curves. Now, the fact that this total difference, the kinetic energy that this 50 grams of minus 10 degree ice has compared to the total energy that the 50 grams of 110 degree steam has is a lot. How much is it? It's equal to the sum of the steps. This is step number 1. This is 2. This is 3, 4, 5. And the fact that the sum of the individual steps is equal to the total, that's called Hess's law. Hess's law. We refer to that mostly using chemical reactions, but this is an example, a practical real-life example, where it's also true. So it's really not very difficult to do these things. It's just a matter of keeping it straight and keep organized. I like to do them right here along with the things. I like to actually label my steps. But anyway, you can take a look at this and look over it, and we'll have a little quiz on this. And I'm going to give you the exact same thing, change these temperatures and change the mass. But otherwise, they're all the same. Got it? All right. Remember, you're lucky.